Okay, so Calc 1 students, I'm going to try to clarify this stuff with differentials for you here a little bit so you can get a little help with what you're doing on your homework. And the homework actually on differentials is pretty straightforward. It really is. Oh, what happened to my OneNote? There we go. Okay, so we're going to go over this diagram and I'm going to talk about what this differential formula is saying here. All right. So I'm going to try to clarify what this is saying. So first of all, we start off with a function. See, this is the function in black right there, y equals f of x, right? And what we have, of course, is f prime of x is just going to be the slope of the tangent line at that particular point. Okay, that's why we've got this line right here to represent the tangent line right there. All right. Now, what we're going to look at on here is what happens is delta x is just some positive number. All right, so what we're doing is if we do x, if we move over delta x, we're just moving over on the function a little bit to the right because we're adding to x. So if we do dx and delta x are kind of interchangeable, they mean the same thing. So if I do x plus dx, that just means that we move over here and then the function value is now here. So one thing that's worth writing right now on this diagram is if you go over like this, there's two things that are probably worth doing here. If you go over like this, that would be, f of x, whatever x is. Okay, so like if x was equal to 2, well, then this would be f of 2. Okay, well, if we move over to x plus dx, and we move up to the function and move over, then this would become f of x plus dx. Okay, so for instance, let's just say that dx is some small number like 0.01. Well, then this thing would become f of 2.01. That's kind of the idea. So in this diagram, let me try to show you kind of what's going on with this problem then. So this distance between these two things here, we would call that delta y. That's the distance, that's the mathematical distance between this function value and this function value. So if you look at this formula, that's what that piece right there is saying, is delta y is the same thing as the difference between these two function values. Okay, so that's the difference in function values. All right, now, if you look at this a little bit more clearly, then dy would be this piece here, okay? That we're talking about how the tangent line changes then. So what happens on this is, remember, this is a slope of a tangent line on here. So if you were going to move over, as we're doing there, then this part right here would be dy. See, this is dx, this becomes dy. We're just comparing this and this, and what we're doing is we're getting a slope of a tangent line, which would be rise over run, which would be dy over dx, okay? So what happens is, if you look at this, then you're going to see that delta y is actually close to dy. They're almost the same. They're off a little bit. Actually, this little slice right here would be kind of what we would call an error in the approximation. So we use differentials to approximate. All right, so that's what that means. So this is saying, okay, this little piece here, this delta y, is close to dy. Okay, which is the same thing as f prime of x times dx. All right, so that's kind of the idea there, is where this formula comes from. That's a difference that approximates dy, so it's equal to f prime of x dx. That's the idea. Okay, and one other thing I want to mention on this is dy over dx. I want to kind of explain what this is saying right here. dy over dx, if you look at this diagram, is a rise over a run. So what it really is it's the tangent line's slope. That's the slope of the tangent line. So just look right here. If you're going to find the slope of this red line, that would be the rise would be dy, which would be that, and then the run would be dx would be that. So that's a ratio of rise over run, so it's a slope, okay? In this equation, what we have is we have dy, well, what is that? That's approximated by the derivative. All right, and let me explain one more thing on that just a second here. Okay, sorry I had to pause because I'm seeing footsteps on my office window. It looked like Batman's here, but it's a window cleaner. Somebody's dangling offside of a rope out there, and I'm on the third floor. So Batman has arrived. All right, so let me explain what's going on here. Okay, and actually it's pretty simple. The dy, dy over dx is used interchangeably to represent the derivative. And what you can do on this is you can multiply both sides of this equation by the differential dx, and what you end up getting is you get dy is equal to f prime of x times dx. Okay, so if you look at this now, like we said, delta y is approximately the same thing as dy, but dy is just f prime of x dx. So that's how that kind of works out then. All right, so that's pretty abstract. You want to study over that diagram and see if you can make sense of this. Just think of these two things as being very close to each other, delta y and dy close, and this little piece right there is the error. Okay, it's off by that amount, and it depends on how big dx is. If you notice on this, if you think about this, if dx got smaller, wouldn't that error get smaller? See, that's kind of the idea of what you want to grasp there. Okay. All right, so let me go through this example down here at the bottom and just kind of talk through this. So what we're going to do is we're going to use the notation of differentials to write this given a small change dx. All right, so we have the function f of x is equal to 3 cosine squared of x. So we're going to do the differential of this in that notational system. So I'm going to write this as f of x equals 3 cosine x squared, and then we'll use the chain rule to get this derivative. Okay, so what we do is we do 3 times 2 times cosine of x to the first power, and then we're doing a chain rule, so you also have to multiply by the derivative of the part that's inside. So it looks like what you're going to get is 6 cosine x. We know the derivative of the cosine is negative sine x. So what we get is we get f prime of x is equal to negative 6, and I'll write this as sine x cosine x times dx. Okay, so if you're doing the differential in that notation, then you're multiplying by dx. And that's what this says right here, is if you're doing that derivative with the differential, it's approximated by f prime of x dx. Okay, now there's something they did on this. I took this out of a book, and how they got that is they did this. Okay, this is really negative 3 times 2 sine x cosine x dx. Okay, well, we have the trig identity that you may recall that says that the sine of 2x is equal to 2 sine x cosine x. Okay, like that. All right, so let's see. So that would end up giving us negative 3 times the sine of 2x dx. Okay, that's how that goes. All right, so that's the first part. And then what we're going to do is the interpretation of small change dx in the independent variable x produces an approximate change in the dependent variable of dy equals negative 3 sine 2x. So we're going to look at this kind of thing here. We're going from pi over 4 to 0.1, okay? And that 0.1, if you kind of look back in your diagram on that, okay, that's just moving over dx amount. So that dx, that differential, is a small number that we're moving up like that then, okay? So what we would end up doing on this then is what we're wanting to do is dy. So let me show you what we're going to do here. Okay, so I'm going to show you this a little bit. I'm going to go over what's been done on this, and then I'll explain how this approximates this then. Okay, so we got f prime of x. We got that's equal to negative 3 sine of 2x dx. Okay, that's what dy is. All right. All right. Now what we're going to do is we're just going to plug in the sine of, let's see, we got pi over 4. So we're going to do negative 3 sine of 2 times pi over 4. Then we're going to multiply by the differential, which is the 0.1. Okay, that's your dx right there. So we're going to work this out. Okay, so if we do this, we'd have negative 3 sine 2 pi over 4 just becomes pi over 2. Then we multiply by the differential 0.1. The sine of pi over 2 is 1. And then we multiply that by the differential 0.1. So that looks like you're going to get negative 0.3. Okay. So that's what we end up getting when we're looking at the approximate change. Now I want to do something on the calculator here for a second. So what I want to do is I want to show you the actual change on this, and you'd have to use your calculator to do this. So if we were going to do the actual change, what we would end up doing is we would do, if you kind of go back to your formula up here, we would do this part right here. That gives you the exact change. So we would do f of x plus dx minus f of x. And I'm going to do this on the calculator, all right? So in other words, what we're going to do on this is we're going to go ahead and just focus on this. So we're going to do, let's see, the original function is 3 cosine squared x. Okay, so what we're going to do is we're going to do 3 cosine squared of this part. Okay, we'll just do this on the calculator. That part is pi over 4 plus 0.1 minus the function value. So we're going to plug this in as the function value. So then what we'll end up doing is we'll do 3 cosine squared of pi over 4, like that. So what we're doing is we're just looking at the difference between these two values. Now, if you go back and look at the diagram, see, that's what that is. That's what delta y is, that change, the difference between those two function values. Okay, when we actually do this on the calculator, and what I'm going to do is just write one more step and go to the calculator. This is really 3 times cosine of pi over 4 plus 0.1, and then we'll square that. And this thing right here, again, I'm just going to do this on the calculator. We're going to do cosine pi over 4 squared like that. All right, now let's get our calculator out. Let me put the calculator in radian mode here. Let me pause this just for a second.